Okay, we're now heading into week 6, the last week of summer session B for Calc 1, and we only have 3 sections to cover this week. That's a short week. Don't forget that you have your final exam on Friday, and I've already talked to I've already emailed each and every one of you about how the final exam will work. I'll also make sure that I post an announcement to everybody, but 50% of the final exam will come from weeks 5 and 6, okay? So you have to concentrate on focusing on studying quiz 5 from week 5, and then the homework's from this week 6 for your final exam for 50% of it, and then the other 50% of the final exam will cover from weeks 1 through 4, so concentrate on studying your first 2 exams to study for the final for that. All right, our first section this week is section 5.3, the definite integral. So this looks just like the indefinite integral. The only difference is we have this a and this b here. A is called the lower limit of integration. B is the upper limit of integration. F of x, the function inside, is still the integrand. Dx still tells you that x is the variable of integration. This elongated s still is the integral sign. Okay, so now what we're doing though is we're taking the integral of f from a to b. So that's how we would say this. And I'll talk more about exactly what this is in just a second. Okay, so again, I'm kind of going over these notes because it's important that you understand we're leading up to what's called the fundamental theorem of calculus. So the first theorem is if we have a continuous function, it's always going to be integrable, right? We can say if we have a definite integral from a to b of f of x dx, as long as f of x is continuous, okay, which means it actually can have a few jump discontinuities, which is fine, as long as it's finitely many. We can't have infinitely many, but then f is integrable. Okay, so we can find this integral. So what is this definite integral? That's the important thing. What does it accomplish for us? Well, essentially, and there's a lot of calculus. If you ever took an advanced calculus class here, we'd have to go over and prove all this to you, but this is what Newton and Leibniz discovered, is that when we're trying to find the area under a curve over an interval, so from A to B, these are called Riemann sums. So if you look at this one you're probably somewhat comfortable with. This was taking the limit as n approaches infinity, where we let n be the number of rectangles. So we put rectangles under that curve. So the height of each rectangle is f, the function value, times the width of it, delta x. So this was saying let the number of rectangles go to infinity. This guy is another notation that Leibniz used mostly, and you don't see it in a lot of calculus books these days, other than to remind you that the notation means that this notation is, instead of saying the number of rectangles goes to infinity, this notation tells you that the width of the partitions goes to 0. So it's the same idea. So in other words, what were we doing? Well, we were finding the area under the curve from x equals a to x equals b. So that's what this is a shorthand notation for. And the fundamental theorem of calculus will allow us to evaluate this a lot quicker than actually going through all that rigorous work we did with coming up with areas of the rectangles and then letting n go to infinity and taking a limit. There'll be a much quicker way to evaluate it. Okay? Also, I just want you to understand that, x here is just a variable of integration. If I used t or I used u, this would give me the same value whether I used x. You could think of this as having t along the x-axis. It'd be a t-axis, or u along the x-axis. It'd be a u-axis. Okay, so this almost, some people refer to it as like a dummy variable. It doesn't matter whether it's x, as long as I'm integrating with respect to x. The dx is important. Since this is t, dt means I'm integrating with respect to t, so I just think of t as my variable instead of x. Here, u is my variable instead of x or t. All right. One last thing I want to talk about are the rules that are satisfied by definite integrals. The order of integration is important. So if I had a to b, instead I switched it from b to a, then it would be the opposite. Okay, so the order of integration, where this lower limit is and what the upper limit is important. Okay, if I don't have an interval, it's a 0 width, and the area under that curve will be 0. There's no area under a single point, x equals a. If I have a constant in front of the function, it can come out in front. That's pretty simple to understand. And remember, this is really a limit, right? The Riemann sum. So you can always bring constants in front of the limits. The same thing as bringing constant out in front of the integral sign. If I add or subtract 2 functions, I can break it up into 2 different integrals. If I go from A to C, then I can instead break it up from A to B and then B to C. All right, so that's what this additivity property means. And these are a little bit less important right now, so don't focus too much on 6 and 7 other than knowing that this property, the maximum inequality, means if I take the area under the curve, the best way to see this is to go down and look at the picture here. The area under f of x right here, well, that's certainly less than this, more than this rectangle, which is the minimum value of f as its height times b minus a, and it's certainly less than the big rectangle, which is the maximum value of f times b minus a. So that's all that property is telling us. And this one says that if f is bigger than g everywhere, then the integral of f is certainly bigger than the integral of g. Okay, so those are the last two properties. So as a first example here, example 81, let's express, I'm going to do examples 81 and 82 together since they're both short. No, I'll just do 81 right now. Example 81, express the given limit as a definite integral. So all I want you to do in this case is understand what this notation means. This notation tells you that we have an integral, right? This is the limit as the width of the partitions goes to 0 of the sum of a bunch of rectangles, where the height is 2 times c sub k cubed times delta x sub k. So this part is your function. You would call that, you just put an x in for c sub k. So that's 2x cubed. The delta x sub k becomes dx. And then I just need to know where my interval is from a to b. So a is minus 1, b is 0. So it's the definite integral from minus 1 to 0 of 2x cubed dx.